the chain rule. So remember that earlier in the term, we looked at something called composite functions. With composite functions, we are plugging one function into another function. So the generic way that we wrote composite functions was y equals f of g of x. Both f and g had their own functions, but we took the second function, g of x, and we plugged it in to f of x everywhere we saw an x. From there, we were able to get a new function. Now we need to consider how we might take the derivative of a composite function. In order to get to the rules that we're going to use to take the derivative of composite functions, let's do a little analysis on the composite functions that we've looked at before and see how we can derive the rules we're going to use. So, considering the function f of g of x, I'm proposing we can rewrite this as y equals f of z, where z equals g of x. So essentially what we're doing here is we're decomposing the functions, only instead of composing them both in terms of x, we are now calling the second function g. That helps us determine the order that we're plugging things in. So here what's happening is that g is our inside function, and our inside function we're calling z. Also, we're assuming here that f and g are continuous differentiable functions. We talked a bit about continuity when we talked about composite functions and setting up the domain for composite functions. That all applies here too. Okay, so now if we make a small change in x, that is going to result in a small change in z. Remember when we talked about continuity, we liked functions that were continuous because the result of a small change in the independent variable resulted in a small predictable change in the dependent variable. That's what's happening here. So a small change in x will result in a small change in z. Now also, a small change in z will result in a small change in y. So again, this idea that these small changes impact the dependent variable in a small way is one of the properties of continuous functions. So if we take these small changes, and as long as those changes are not equal to 0, we get this relationship here, that a small change in y over a small change in x is equal to change in y over change in z times change in z over change in x. Now, here, just like any other fraction, we could see that these delta z's could cancel, leaving us with just delta y over delta x. So mathematically, since these small changes represent numbers, these two things are equivalent. What's really important here, however, is that these differences, these ratios of differences, are also the things that we take the limit of when we're looking for the derivative. So if we take the limit of all pieces of this, what we get is a really interesting rule that's going to give to us the chain rule. So let's take a look at that. So again, when we take the limit as the difference goes to 0, we get these different derivatives. So we get dy dx, the derivative of y with respect to x, which came from this difference quotient, is equal to the derivative of y with respect to z times the derivative of z with respect to x. Now, this may not make sense without actual functions, but we'll do plenty of those later. The idea is that we can take these derivatives using the formulas we used in the last couple sections, and we can multiply the derivative of y with respect to z times the derivative of z with respect to x to get the derivative we ultimately want, the derivative of y with respect to x. Another way that we can write the same thing is we can write that the derivative of f of g of x is equal to f prime of g of x times g prime of x. This actually says the same thing as what it does above. So dy dz, the derivative of y with respect to z, is f prime of z. dz dx is the derivative of z with respect to x. Remember, z was our g function, so that's g prime of x. But remember that z is g of x. So therefore, we get this formula, f prime of g of x times g prime of x. So there's two different ways we can write the formula for taking the derivative of a composite function. The first is with the Leibniz notation up here. dy dx equals dy dz times dz dx, or with the Newtonian notation down here, that the derivative of f of g of x is f prime of g of x times g prime of x. We're going to use both of these formulas in different ways, and the one that you're going to use is really dependent on the information that you have. But before we get to using the formulas directly, let's look at a situation where we would even want to use these formulas to get some sort of derivative using the chain rule. Suppose that the amount of gas that a vehicle uses, G, given in gallons, depends on the distance traveled, S, in miles. This makes sense because the amount of gas that you use when you drive something depends on how far you drive. Now, the distance traveled, S, is going to depend on the time T in hours that the vehicle is driving or moving. This also makes sense. How far you go depends on how long you've been on the road. Now, if we know that 0.05 gallons of gas is used for each mile traveled, and that the vehicle is traveling 50 miles an hour, then we can use this information to calculate how fast the gas is being consumed. So we want to know how many gallons per hour we're using. So the rate that we want is dg dt. So here again, we want to know how many gallons we're using for each unit of time, which is in hours. What we know, however, is the other two rates. We know dg ds, which is going to tell us the gallons per mile, which again, we got in the first part. Gallons per mile. So G, capital G is gallons, S is in miles. So this is 0.05, and we'll write the units underneath. Gallons per mile. We also know ds dt. So ds dt is going to give us 50 miles an hour. So it's how quickly our position is changing in miles over time. So 50 miles per hour is our ds dt. So we're multiplying here, 50 miles per hour. And so if we multiply these two numbers together, 0.05 times 50, we get the number 2.5. And now let's check out the units. So here we have gallons per mile, and here we have miles per hour. So the miles units are going to cancel. And that means that the units of our 2.5 here are going to be in gallons per hour. And that's what we were expecting, because dg dt, we know that the capital G represented gallons, and dt, time, was in hours. So we were able to use the two derivatives we knew, dg ds and ds dt, to find out information about the derivative we didn't know, dg dt. So here is an application of the chain rule where we're trying to figure out information using rates we have to find out information about the rate that we don't have. Now, when we do the chain rule, we're going to do all sorts of applications. And like I said, we're going to be using the formula in various ways. So we're going to start with two applications that don't actually use any formulas yet. We'll get to those later, but instead use the general rules that we have for the chain rule. Example 1. Use the information from the table below to answer the following questions. A. Determine if y equals f of g of x is increasing or decreasing at x equals 3. B. Determine if y equals g of f of x is increasing or decreasing at x equals 3. And we remember from our earlier section that order is important and that these represent two different functions. And part C, we're going to find the equation of the tangent line to f of g of x at x equals 1. I've rewritten the formula here that's going to be most useful to us when we do it. So here it's going to make more sense to use the Newtonian notation since our table reports things in that way. So for part A, if we want to figure out if we're increasing or decreasing, we can use our first derivative. Remember, if the first derivative is positive at a point, your original function's increasing. If the first derivative is negative at a point, then the original function's decreasing. So here, if I consider the derivative, I know that my derivative is f prime of g of x times g prime of x. That's my general formula. But now I want to know what's happening at x equals 3. So I want to consider f prime of g of 3 times g prime of 3. Now, two of those things that I see here I can find on my table. G of 3, which is inside the f prime function, I can go to the g column here. I can go down to number 3, and I see that that has a value of 2. So that means I can substitute that in. So I'm looking for f prime of 2 times g prime of 3. Well, g prime of 3 I can also read off my table. So if I go to the g prime column here, and I go down to 3, I get that g prime of 3 has a value of 1. So finally, I need to find f prime of 2. So here if I go to f prime, and I go down to an x value of 2, I get negative 1. So here I have negative 1 times 1. And that equals negative 1. So I know that my first derivative of f of g of x, the first derivative, is going to be negative when x equals 3. If my first derivative is negative, that also tells me that the original function is decreasing. So I'm able to use my general chain rule, plug in the values, and use my table to approximate all the values I need to solve this problem. Let's do part B. So we want to determine if y equals g of f of x is increasing or decreasing at x equals 3. So we're going to do something very, very similar to part A, only now the order of my function is a little bit different. So when I take my derivative, my outside function now is g. So I have g prime of f of 3 times f prime of 3. So since f is my inside function, that's the one that I'm multiplying on the outside as the derivative, f prime of 3. So again, I want to find the values that I can see here. So I have g prime, and now I'm going to look up f of 3. So f of 3, I'm going to my f column, I go down to the number 3, and I get 2 as my value, times, now f prime of 3, I need to go to the derivative column, f prime of 3 is going to give me a value of 5. And I have to keep going because I still have more things to look up. So now I have to look for g prime of 2. So I go to the g prime column, and I go down to the x value of 2, and I get negative 3. So my final calculation is negative 3 times 5, which gives me negative 15. So again, if the first derivative of my function is negative at a point, that means that my function has to be decreasing at that point. Part C. Find the equation of the tangent line to y equals f of g of x at x equals 1. So remember, when we want to find the equation of the tangent line, we need a point and a slope. The way that we get our point is by plugging our x value into the function to get the corresponding y value. So that means we need f of g of 1 to get the y value for my point. G of 1, if I go to my g column and x equals 1, is 3. So that means I'm looking now for f of 3. F of 3 means I'm going to go to my f column, and I go down to x equals 3, and I get a value of 2. So that means when x equals 1, y equals 2. So I have the point 1, 2. Also for the equation of the tangent line, I need the slope of the tangent line, which means I need the derivative of the function at x equals 1. So again, using the chain rule, I'm going to be calculating f prime of g of 1 times g prime of 1. So again, I'm using this notation here for the chain rule. I'm going to start looking up these values. So the first value I'm going to look up is g of 1. So g of 1, I go to my g column, I go to x equals 1, and I get a value of 3. So I have f prime of 3 times g prime of 1. So g prime of 1, I go to my g prime column, I go to 1, and I get a value of negative 4. I need to keep going. F prime of 3, I'm going to go to my f prime column, I go to a value of x equals 3, and I get 5. So finally, now that I've found all the things I need here, I have 5 times negative 4, which is going to give me negative 20. But remember, that's the slope of your line. So now I need to put this all together to find the equation of my line. So I'm going to come up here in this box on the right. So far, I have y equals negative 20x plus b. I'm going to plug in my point, 1, 2. So when x is 1, y is 2. So I have negative 20 times 1 plus b. So I'm going to add 20 over here, and I'm going to get that b equals 22. So the final equation of my line is y equals negative 20x plus 22. So similar to what we've been doing before, only now when we have to find the slope using the derivative, there's a couple extra steps when we're doing the chain rule. Let's look at another example. Example 2. If h of x equals f of g of x and k of x equals g of f of x, use the graph below to find h prime of 1 and k prime of 2. So let's start with h prime of 1. So the derivative at 1, h prime of 1, is going to be f prime of g of 1 times g prime of 1. So again, I'm just applying the chain rule formula with x equals 1 here. So I need to figure out which of these values I know and which of them I need to compute. So g of 1 is something I can read off my graph. So g of 1 means I'm going to go to x equals 1, and I'm going to go up and find the corresponding y value, which appears to be 7. So I'm going to write this as f prime of 7 times g prime of 1. So I notice here that I don't have a graph for the derivatives, which means I need to figure out a good way to find the derivative of each of these functions. Now I can approximate the derivative using points around the point I'm interested in. However, I notice that these functions are linear. And if I think back to my derivative rules about linear functions, I know that if I can figure out the slope of the line, that the derivative of this function is going to be the slope of that line at every point, because the tangent line will always have the same slope as the line. So here, if I want to find the slope of f of x, I can pick 2 points. So here I'm going to pick the point 0, 2 and the point 2, 6. So I have 0, 2 and 2, 6. So if I do the change in y over the change in x, I'm going to have 6 minus 2 divided by 2 minus 0, which is going to give me 4 divided by 2, which gives me 2. So the slope of my line is going to be 2 at every single point. And since the tangent line lies on the line, that means that the derivative is 2 for every single point on f of x. So that means at 7, f prime of 7, the slope is 2. I can do something similar for g. So again, I want to compute the slope of the line. So I'm going to pick 2 points on the line. I notice here that I have the point 0, 8, and the point 8, 0. So again, I'm going to do change in y over change in x. So I'll do 8 minus 0 over 0 minus 8, which tells me that the slope of this line is negative 1 at every single point. That also tells me that the derivative is negative 1 at every single point. So g prime of 1 is going to be negative 1. So multiplying those together, I get that h prime of 1 is going to be negative 2. So again, I don't know the function f of x or g of x, but I'm able to talk about what's happening at the composite function because I have the graphs. I could take the time to get the equations of the lines, and then I would have g and f, and I could make the composite function and take the derivatives that way. But here I'm doing the analysis without finding the specific formulas. Let's do this next one, k prime of 2. So k prime of 2 means that we are going to be going and we're going to be looking at g of f of x. So that means when we take our derivative, we're looking for g prime of f of 2 times f prime of 2. So again, we want to see what values we know. So f of 2, we can go to 2, we can go up until we hit the f function, which is in red, and we can find that value, which is 6. So now we have g prime of 6 times f prime of 2. So again, if I'm looking for the derivative, g prime of 6, I know that the derivative is going to have to be the slope of the line, which I already found in the first part. So I know that at 6, the slope has to be -1 because everywhere on g has a slope of -1. And then f prime of 2 is going to have a slope of 2 because f has a slope of 2 everywhere. So multiplying those together, I again get -2. So I want you to think about whether or not this would be a coincidence. Do you think if I tried h prime of 4 or k prime of 3 that I would also get -2? Am I always going to get -2? And if so, why? These are good things to try out if you're not sure what the answer is going to be. So next we're going to move into the formulas for the chain rule. There's lots of different formulas depending on the type of functions you're working with. So we'll look at each of them carefully and individually so we can get used to computing the chain rule for things like power functions, polynomials, exponentials, natural logs, and trigonometric functions.